Good afternoon and welcome to Purdue University and the CERIAS Computer Security Seminar. Our speaker today is Ashish Kamra. He's a student of Professor Elisa Bertino of Computer Science and Professor Guy Lebanon of Electrical and Computer Engineering. Ashish is a PhD student in Electrical and Computer Engineering. His research thesis area is in database intrusion detection and response. And his topic today is responding to anomalous database requests. Ashish?
Thank you, Randy, and welcome everybody to my presentation. My name is Ashish Kamra, and as Randy has described, and I'm going to present this work, joint work with Dr. Bertino, my advisor, and Rima Neme. Rima is again a PhD. Oh, it's right there. Rima is again a PhD candidate in the computer science department. Okay, so let's start. So the agenda of the talk is going to be, I'll define the problem that we are trying to address here, then some background on the problem and some motivation, and some kind of high-level overview of the approach that we are taking. I'll not go into all the details, and some little bit of experimental results, and then we'll discuss some of the future work related to this line of work, and then I'll be open to all your questions. So very simply in one slide, what I'm trying to build here is an integrated anomaly detection and response mechanism for relational databases. And we'll expound upon that as we go in the presentation. But the key word here is that we are trying to build an anomaly detection model, and integrated means that we want to have it inside the database system, not as a software not as a software system which is outside the database. It has to be inside the database server, and it's an anomaly detection model. So what is the motivation behind having this kind of thing? So there are essentially two questions that will provide you with the motivation. First is, why do you need an anomaly detection system? And second is, why do you need it tailored for relational databases? And I don't think I have a slide for why do we need a system, anomaly detection system which is specific for relational databases, but maybe that will come upon somewhere down the line in my presentation. Okay, so why do we need an anomaly detection system first? So there are a lot of data protection acts these days which regulate how the companies should maintain and store access to their data. So there are acts such as SOX, Sarbanes-Oxley, which is applicable to any companies which is publicly listed on the stock exchange. There is HIPAA, health related to patient medical data, and that's applicable to any organization that deals with patient data, and including Purdue, because Purdue has a push center. And GLBA is Graham-Leach-Bailey Act, which is applicable to any organization that stores financial data, and that includes Purdue also. So they have these acts have got many protections, regulations, whatever, but we are concerned about the provisions they have for data management. So they specifically ask you to record who is accessing the data at what time, when is the data accessed, where is the data accessed, and this is actually means you have to audit all kinds of data usage, and again prevent unauthorized access and modification to data. And very high level specifications are specified by these particular acts. So now the question you might have is, but don't we already have an auditing mechanism inside databases to address this? And of course there is. And don't we already have an access control system in place to prevent unauthorized access to data? Yes, we do, but we still have the problem insider threats. Insiders are malicious employees who have the necessary privileges to access data and manipulate data, and it's very hard to predict when trusted employees can go malicious and indulge in malicious activity. So we need an anomaly detection model, and the kind of model that we propose will become clearer in next few slides when we discuss the system architecture. Again, if the databases are accessed by applications, you have the problem of SQL injection. Now, SQL injection traditionally is an application level vulnerability. What happens very simply in a SQL injection is that you have an application that is interfacing with a database, and it accepts some user input, and it uses that user input to form SQL queries dynamically. Problem comes when like most software vulnerabilities, that the user input is not sanitized before you form the SQL query, which can allow a malicious user to form to submit a query to the database that is different from the original query intended by the application. So that is SQL injection. So a lot of solutions are there to address SQL injection at the application level, but we also believe that solutions must be devised at the database level also, where the data owners have no knowledge of what kind of application is accessing their data, and they are just providing a service as they are just providing data access as a service to applications. So they should have some solution at their end to detect a SQL injection attack. And we also propose some anomaly detection model to detect SQL injection attack. So these are real problems. It's not just I'm making insider threats and SQL injection up. Just to quote one particular survey, insider threats have been identified as the second biggest threat by organizations after hackers. And again, one of the findings of the survey was that majority of the incidents were detected only after the attack, that's in caps, and through manual procedures. So there really is a need to have automated systems for detecting insider threats attack to databases. And there are some real solutions as well. So you have a lot of third-party database access. Okay, actually should be database activity monitoring product. Anyway, so a lot of third-party commercial database activity monitoring products are there in the market. I just listed 3 of them. There must be more than at least a dozen that I can list. But these are, I guess, the most popular ones. And why I'm calling them as third parties, of course, you understand that they are outside the main database system. Interface between, they look at all database, all traffic going to the data center, and do auditing, do intrusion detection, anomaly detection, whatever they claim to do. But the goal of my work is to have an anomaly detection and, again, a response system built inside a database server, which is a problem that has not been addressed by the database vendors as yet. And the key reason is that because how is it going to affect the performance of the system, of the database system, which is very crucial. But we'll see. I don't have any experimental results for the performance yet, but towards the end of my work, probably I will. So now I'm going to go into some of the details of our approach. And this is a very high level overview of the system architecture. You have, let's look at the training phase at the bottom. So you have a profile creator module which can create profiles of users or applications that submit queries to the database, or it can also read queries from the audit log, assuming you have turned on auditing on the database system. And it comes up with some profiles. Now, precisely what these profiles are will depend upon the kind of threat model you have in mind for anomaly detection. Okay, so let's assume you have the profiles with you. Then that's the training phase. You learn the profiles over a period of time. And in the detection phase, for every new query submitted by the user, it goes through a feature selector which selects the features from the query. And again, the feature selection is dependent upon the kind of anomalies that you want to detect in the query. Now it goes through the detection engine, which is going to look at the profiles and apply some intelligent algorithms to come up with an assessment of the query. Now the assessment could be, okay, it doesn't think the query as anomalous, or if it thinks that the query is anomalous, it's going to submit an assessment to the response engine, and the response engine is going to look at some predefined response policies and come up with an appropriate response action to the anomaly. Now, okay, so this is the high level. Yeah.
This happens for every query that is issued.
in the detection phase is supposed to happen for every query. And there again the question of performance comes into picture. How is it going to affect that? But unfortunately, the system is not there yet, where I can give you some answer on that. But of course, that's a very big concern. So what are the detection tasks we are looking at? So I have identified 3 kind of anomalies that you can have in the database system. You can try to detect anomalous access patterns. A particular application or the user only accesses certain portions of the database. Now I'm assuming here that the principle of least privilege is not there in the first place yet, that the user has more privileges than he requires to carry out his normal tasks, and which is, trust me, is very much the case in real systems. So you want to see, normally he accesses this particular portions of database, and when for a new query, if the access performed by a new query is in let's say in harmony with his previous accesses. Otherwise, it's termed as anomalous. So, but I'm not going into detail of this anomalous access pattern system. Then SQL injection, as I described. So that's again you can model that as an anomaly detection problem. Then there is again something called as query flood attacks, where an insider floods the database with a lot of queries and leading to denial of service for other legitimate users. So this problem can also be formulated as an anomaly detection problem. But what I'm going to speak in little bit in more detail in this presentation is about an anomaly response mechanism. Okay. Now, what are the problems with a response system? Let's say. So you have a user, submits a request, detection mechanism, okay, detects that it's an anomaly. Now, what are the response options available for, let's say, the response mechanism? It can log the request and that's it. It can send an alert. I'm not sure if it's that visible, but that this particular thing is sending an alert to the administrator. And typically these two are the most popular response actions. Or if you go further in context of database system, you can revoke the access of immediately revoke the access of the user. You can abort the current transaction. So the key question is which response option to choose. Some of them are kind of benign. You send an alert, you log. Some of them are aggressive. So the question is which response option to choose. That's a very difficult problem. We are trying to address this problem by using a policy-driven response engine. And some of the details will come up in later slides. And the second problem with the response mechanism to date is, so you have response options which I just show you. Some of them are aggressive, like abort the request. Deny is you deny the privileges to the users, which you think are anomalous, or you revoke those privileges. So I'm not going to the semantics of deny and revoke here, but there are 2 different responses you can take. Or you can just disconnect the user session. So all these are very aggressive response actions because they are going to interrupt the user query. Or you can be very conservative and you can simply log, or you can send an alert to the administrator. The problem is, can we do better than of being very aggressive and being very conservative? And we address this problem by introducing the notion of fine-grained response actions using the concept of privileged state transitions. Okay, so much far. So what is a privileged state I'm talking about? So we propose that a privilege assigned to a user or a role in the database can have a state associated with it. If you want to think about it, right now you can think about a privilege can be in a binary state. Either it is assigned to a user or not assigned. So we say, okay, you can have more states assigned to a privilege, assigned to a user. So these are this is the state transition diagrams that we present in this work. Let me just explain it a little bit. So you start with a privilege. If it's assigned to a user initially, the state is clean. So I think in the later slide I present what is meant by privilege suspension and privilege tainting. Okay, so let me go to that slide first actually. So what I mean by privilege tainting, so you can go to the tainted privilege state from clean, right? So let's just first see what you mean by privilege tainting. It's a very simple concept. The request still goes through. If you mark a privilege as tainted, the request just goes through. But so it essentially means that the detection engine does not have too much confidence in the anomalous request, in the anomaly that it has detected. So the response, and that has to be conveyed to the response engine in terms of, let's say, a confidence parameter of the anomaly assessment. So the response engine, you can have users can define a policy to mark the anomalous privilege in question as tainted, and now the tainted privilege state can be used to for other policies to specify more stronger response actions. Like for example, if you see that a lot of privileges are getting tainted, so you can have a policy which will show later what policy looks like. You can have a policy which will say, okay, now the privilege should be revoked or denied. So that's a less severe form of response action which can be which can be used by more stronger response actions. Then there is again something called as privilege suspension, which is a little bit more stronger than privilege tainting. So you suspend a privilege which is so the request is blocked unless a confirmation action is performed by the user. So you put the privilege in suspended state, or assume that if a user request comes and the privileges that it is asking for are in suspended state. So what's going to happen is the system is going to ask the user for a confirmation action such as re-authentication or a second factor of authentication. This can be guided through a policy mechanism, and if the user passes that confirmation step, then further actions can be taken. If it fails, then stronger action can be taken. If it passes that thing, then the request can be allowed to go through and the privilege can be moved back to the clean state. Okay. So I guess this is what I have to say about privilege suspension and privilege tainting. And once you specify state for privileges, it's going to introduce complexities in the working of the access control mechanism. So you can build upon this work upon how to have a nice access control, a formal model of an access control system which incorporates the notion of privilege states. Okay, so now I'm going to talk about when a detection mechanism detects an anomaly, it's going to submit an anomaly assessment to the response mechanism. So how what is the anomaly assessment going to look like? So it's going to submit the anomaly assessment in terms of two kind of attributes. One is contextual, another is structural. And what I mean by contextual anomaly attributes are they describe the context surrounding a particular user request, such as the user executing the request, the role or the roles is associated with that user at that particular time, the source from where the request is coming, and so forth. And the structure is the actual structure of the request. So which database it is accessing, in that which schema it is trying to access, what are the objects like tables, views, stored procedure, what the request is doing, and the attributes, again, they will differ depending upon the objects that are accessed, and then again what SQL command was used in the request. So these anomaly attributes kind of act like an interface between the detection mechanism and the response mechanism. And when we talk about a response policy, we are going to define a policy based on these attributes itself. So we're going to just look like in the next couple of slides what a policy language looks like. So it's a event, condition, action kind of a policy. An event here is an anomaly detection event in the system. And if some conditions are satisfied, and what I mean by condition is one particular condition is an atomic predicate defined on an anomaly attributes that we just saw in the previous slide. And examples of conditions are listed below. So they are just simple predicates. And then we say that the conditions is a conjunction of these predicates. So if all of them are satisfied, then you can take an initial action based on whatever is specified by the user. Now this is the typical event condition action kind of a policy paradigm. We go a little bit further and say, because we want to give a high level language to the user to specify these policies. So you say, okay, if the initial action is, let's say, privilege suspension, then you can, in the policy itself, specify what is the confirmation action that needs to be taken, and again, what is the alternate action to be taken in case the confirmation action fails. So let's look at an example of a particular policy. Let's say a policy says that re-authenticate unprivileged users, so non-DB owner kind of users, who make a connection from inside the organization internal network with a second password for write anomalies to tables in the DBO schema. Now this is after some anomaly has been detected by the detection engine. So in terms of the policy language, how this policy can be expressed is like this. If role is not equal to DBA, that gives you unprivileged users. You have the source IP in some particular range which represents the internal network of the organization. An object type is table, and okay, the syntax of the attributes is a little bit different, but I hope you get the meaning here. And objects in this particular schema, and the SQL command, because you are looking at write anomalies, so we say insert, update, delete. Then the initial action is to suspend the privilege, and confirmation action is re-authentication with a second password, and the alternate action is otherwise to disconnect the user. Okay, so I hope this is up till this point it's all clear to you. So we implemented the system in PostgreSQL open source database. So we designed a schema for storing this policy. So table structure so we store the policies in a database, in database tables, and we then have a policy selection algorithm for once you have the anomaly assessment in terms of the attributes, how you're going to select this policy from the policy tables. So I'm not going to go into the details of the implementation here for policy storage. And so one particular anomaly assessment can match multiple policies. So in that case, which policy are you going to select, and which response action are you going to execute? So it's a hard problem, but we kind of do some cheating here, and we say, okay, you can specify. You give options to the user. You want to choose the most severe policy, where the policy severity is actually dependent upon the severity of the response action, where you saw that you can have aggressive actions and conservative actions, and in between fine-grained actions. So that guides the severity of the policy. Or you can have a least severe policy. So ultimately you choose just one policy, and then you choose the response action to execute. And then we implemented the notion of privileged states inside PostgreSQL. Just to give you a little bit of flavor on that, PostgreSQL maintains privileges. So it's got, at the max it can have 16 privileges. So it can fit all privileges in a 32-bit integer, and it maintains that as an ACL item for each database object, where the first 16-bit specify the privilege bits, and the rest of them are the ground options. So a particular bit, so every privilege, like select privilege, has got a particular bit mask, and the same position in the ground option bit specify that particular privilege is grantable or not. So very nice, but of course this is only possible if you have just 16 privileges. So you can pack everything in a 32-bit integer. So we just extend that we use the same data structure for privileged states, and we specify, okay, you have another data structure called ACL state item, where if a particular bit at, let's say, bit number 1, which is equivalent to the bit mask of select privilege, so it's tainted, and similarly for the suspended bit. And you attach again this to the database objects in the data in the database. So now I'm going to go over some of the experimental results. The objective of the experimental evaluation that we performed was to evaluate the efficiency of the policy storage mechanism, which I did not explain, and the policy selection procedure, policy selection algorithm, which again I did not present. But I think the couple of slides will just give you, okay, what was the setup? So implementation is PostgreSQL 8.3. We generated policies randomly. You select attributes and you randomly assign values to attributes, and that's how generate synthetic data. And the policy selection code was in the PL procedural language of PostgreSQL, which is PL/PGSQL. So we didn't write it in C, which would have been much faster. But anyway, just to see how it looks like. So the first experiment gives you a graph of how the policy selection time, what the policy selection time is as the number of policies increase, which is kind of unrealistic to think that you will have 1,000 policies in the database. But this gives you an idea that the policy selection time remains constant, and that is very good in terms of the scalability of the system. So you keep adding policies to your mechanism, the selection time is going to remain constant. And it's 20 millisecond, around 20 millisecond in this case, but it can be brought down lower if you write your code in C instead of PL/PGSQL. And then, but as number of policies, the second graph is between number of matching policies and the policy selection time. So as the number of matching policies increase, you have a linear increase in the policy selection time, which is, I think, is also reasonable when we talk about the scalability of a system. Okay, so lots of future work in this direction. So the policy storage scheme that I did not describe, we need to, right now we can only support equality and non-equality predicates. For supporting wider range of predicates, we need to come up with a better scheme. And as I said, you can develop a formal access control model based on the notion of privileges, which is again a work in progress right now. I guess that's all I have to say.
Questions? Do you have an idea of what kind of overhead this adds to the database management system? Just accessing data, which should go, if that's in, what do you imagine an order is on top of that?
Well, that's what the policy selection algorithm experiment. So you see, could be at least 20 milliseconds if you just look at this experiment.
But relative to just a simple access.
That's a very difficult question to answer. It's going to depend upon the system under consideration. So I need to run some actual benchmark simulations to see how, in terms of, like you're asking, percentage wise, how much is going to increase, affect the performance of the system. But I don't have precise number for you. Yeah.
What would you consider an acceptable kind of threshold or an acceptable amount of overhead?
That should actually depend upon the system under consideration, but let's say for a normal database, less than 5% should be good. But yeah.
Let's say in case of SQL injection, the query that's actually going to be formed, it may not be like harmful sometimes. It just manipulates the query to be something like a Boolean, and so that you just get unlimited access to the database.
Okay.
So in those conditions, like what kind of policies are you looking for to actually find an injection that's coming in?
See, that's the thing. That's a good thing with an anomaly detection system. So right now you will have the approaches you have for SQL injections are specification based. You try to specify all kind of malicious queries that you can think of, but that's really not possible because the space is kind of infinite with SQL injection. So with anomaly detection, the advantage is that you have a model of your normal behavior, and anything that deviates from it, it may not be malicious, but you think that it's worthy of more investigation. So you flag that off as an anomaly. So the case that you describe exactly fits the scenario. The query looks, you are just appending a Boolean predicate at the end of the query and looks pretty innocuous, and it will pass most specification based intrusion detection system. But an anomaly based system, if you design it carefully, if the model that you build can actually detect that particular query as anomalous.
I mean, like, so you have a huge application deployed. You're going to get like kind of a lot of queries.
Yeah.
Where the workload will actually be looking for some kind of check whether the string is present, a lot of. So is there any specific way, like using a transaction, where you can say, okay, this could be a possible, like kind of intrusion?
Again, that's going to depend upon the anomaly detection model, which I did not describe in this particular because this was about anomaly response. But I have some work on creating models for creating anomaly detection models specifically to detect SQL injection attack. Where you, just to give you a flavor, here you define some correlation between the attributes that are there in the projection clause, like the tables access, and the attributes that you have in the where clause. And you store these correlations with you. And you use that to see if the new query just conforms to those correlations or not. In a very brief nutshell, that's what we do.
Have you used your techniques in some production database server
Not yet.
where you could like find out how efficient the performance might be?
Not yet. So the ultimate goal is to have it implemented inside PostgreSQL DBMS, and it's going to require changing the server code for PostgreSQL because the kind of response actions that I have described, they're going to require changes to the access control mechanism of the database. But to answer your question, no, I don't have it implemented inside the database. Which not even product. First, I need to have it implemented inside a database and run some benchmarks. And I guess that should be enough. Yeah.
Thank you very much.